Hello everyone, my name is Nakungu Deborah. Welcome to my other tutorial. I thank everyone who views all the tutorials I usually post on my YouTube channel. For everyone who has not yet subscribed to my YouTube channel, please click the red button on the right hand side of your screen to be receiving other tutorials that I'll be putting on my channel. So today I'm bringing in part 2 of intermediate macroeconomics, and this tutorial is concentrating on the Solow'S growth model as model number 2 under the exogenous growth models. If you did not watch the first tutorial, please first go and view the first tutorial to continue up or to link up with this tutorial. Now, the Solow'S growth model is a modification of the Harrod-Domar growth model. It builds upon the assumptions upon key issues that were talked about or that were represented in the Harrod-Domar growth model. Now, this model is based on an assumption of diminishing marginal returns of factor inputs, implying that as more and more units of a factor input you use, the output will first increase at an increasing rate, then at a decreasing rate, and eventually decline. So if you reach an optimum capacity or level of employing a given factor of production, it means that at a given point in time, the output that that factor input was giving out will eventually decline. Now, this Solow'S growth model is based on assumptions, as we know that if you are building a theory or a model in economics, theories are based on assumptions. Now, the key assumptions that we have or that we look at if we are looking at the Solow'S growth model are as listed below. One is that the growth rate of labor is exogenous. It's more of we are saying that the growth rate of labor is constant, and we shall represent that growth rate of labor as n. We also note that the growth rate, that as the population increases, it implies also labor is increasing or growing. So our first assumption is the growth rate of labor is exogenous, and I said exogenous also means that it is constant. The second assumption we can look at if you're looking at the Solow'S model is that the production function is factor substitutable and well behaved. Now remember that we said that it is a modification of the Harrod-Domar growth model. The production function that we were looking at in the Harrod-Domar growth model was a fixed proportion production function, implying that there was no substitution between factor inputs. But now if you're looking at the Solow'S growth model, our production function is factor substitutable, meaning that we can substitute among factor inputs. It's more of we have a convex production function. If we are to represent it graphically, that our production function is convex. So we can substitute between factor inputs. We can decide if we have more labor, it means that as a farm you can employ labor intensive techniques of production. If you have more capital, then you can employ capital intensive techniques of production. Now we also remember here I've said that the production function is factor substitutable. We know what it means. And well behaved. Now well behaved means that the necessary and sufficient conditions are put to use. Like if we get, because if you're looking at the necessary condition, it means that if you have a given factor, if you have a given production function and then we differentiate that production function, it means that the first derivatives or what we get as the first derivatives must be positive, so greater than 0. Now the sufficient condition is that our second order derivatives must be less than what? Than 0. So the production function under the Solow'S growth model is factor substitutable and well behaved. Well behaved, I've said the first order conditions are positive and the second order conditions are negative, less than 0. Now, our second assumption under the Solow'S growth model is that the market clears. Market clearing is that we always have equilibrium in the market, and they're saying that that equilibrium happens at a point where our savings are equal to investments. We are having the market always clears, there is equilibrium in the market. Our fourth assumption is that factor inputs exhibit constant returns to scale. So if we have, let's say this is our production function, y is a function of k al. Al represents effective labor, k represents capital. But if you look at a alone, a represents technology or knowledge. Now, constant returns to scale means that if we increase factor inputs, let's say by the same amount, the output will increase by the same amount that we had increased the factor inputs. So that is constant returns to scale. If you increase, let's say, capital by 4 units, constant returns to scale means that even output will increase by the same units by 4. So the factor inputs exhibit constant returns to scale. Technology grows at a constant rate. Savings rate is a fixed proportion of income, and this is how it is defined. So those are some of the assumptions of the Solow'S growth model. Now, this is the most important bit. That is the derivation of the model. Now, when we are deriving any model, in modeling our theories of growth, what we need to first know is how is real output determined in the long run. Now, in the long run, how do we define real output? It means that we have to have a given production function, because a production function will show us a relationship between output and the factor inputs. So now it means that before we continue, we have to define our real output. How are we going to define our real output? So that's why I came up with a production function, and specifically in the Solow'S growth model, they used a Cobb-Douglas production function. Now remember, we said that our production function exhibits constant returns to scale. We said that technology grows at a constant rate, and we said that output is a function of capital and effective labor. Now this is a given explicit production function that I'm having here. Yt is equal to k power alpha al power 1 minus alpha. So it's more of we've defined our real output in the long run. That output Yt is defined by capital as a factor input and effective labor as a factor input. So we are using two factor inputs, that is capital and effective labor. So here the note is just showing us what the parameters here we used are. So the K stands for capital, the A stands for knowledge, the L stands for labor. Now the alpha here, now the factor here represents the alpha on K represents the share of capital in the production process, or it's then the 1 minus alpha represents the share of effective labor in the production process. Now for us to before we continue with deriving this model, let us first turn our production function into a per effective worker production function, and we do that by dividing each variable here in our production function by AL, by effective labor. So that's why we have Yt over AL being equal to K over AL power alpha. So sorry about this, but this has the K over AL has to be in the brackets and the alpha outside the brackets. The same applies to AL over AL, and this is supposed to be a multiplication sign, not an equal sign. So like after dividing, we come up with something like that. So this here is not supposed to be an equal sign, but a multiplication sign. We are supposed to be having yt over lt is equal to k over al power alpha being equal to, times a over al over al in brackets power 1 minus alpha. So from here we simplify what we have here by letting yt over al be represented by a small y. And this small y, we call it output by effective work. Like after dividing our yt over al, now that ceases from being just output, but it becomes output per effective worker. Now we let k over al be small k, or b kappa. This symbol is kappa, b kappa, and this is no longer capital stock, but it is capital per effective worker because you've divided by effective labor. Now, since we have AL over AL, they will go, and remember 1 power any number, it remains 1. So from what we did here, we come up with, since this goes to 1, it means that we are remaining with kappa power alpha. So it means that our equation now, or our production function, becomes small y is equal to kappa power alpha. Remember, this small y is yt over al. The kappa is k over al. So this is our new production function. It is the same as the beginning one, but the difference is this is in per effective worker terms after dividing by AL. Now, we derive the Solow'S growth model using some key equations. The first equation is the capital accumulation equation. How is capital accumulated? That our change in capital is equal to our net investment minus the depreciation of capital. So the sigma stands for depreciation and the KT stands for capital. We know that from the previous tutorial. The second equation that is important as we are deriving the Solow'S growth model is our equilibrium equation. Remember, I said the market clears, so we have to have this equation where S is equal to I. Now we also derive our equation from capital per effective worker equation. We said kappa is capital per effective worker, and it is equal to K over AL. That is also another important equation we need to know and have when deriving this model. Then this I is equal to I over AL just shows us that this small I is investments per effective worker. This small s is savings per effective worker. Now, the major key equation we use to derive this model is equation number 3. We should really note this. Equation number 3, this is the first step, or it is the beginning of deriving this model. It's from equation number 3. What do we do to equation number 3? Equation number 3 is showing that kappa is equal to K over AL. So our first step here is, from our equation number 3, we apply natural logs. So if we apply natural logs, we come up with, if we apply natural logs to this equation, we come up with ln kappa is equal to ln K. Remember, in logarithm, if we have division, it means that we subtract. If we have multiplication, we add. So that's why we are having ln K minus, I put the brackets here because we are having a AL as a denominator. Remember, this is AL, A times L, and this will we said, as I told you, in natural logs where I have multiplication, we add. So if you leave this minus ln A plus ln L, if you don't want to put the brackets, then you represent it as ln K minus ln A minus ln L, all of it as minus. But if you still want to show the addition here, you put it in brackets. So now this is our new equation after turning it into natural logs. Our next step after after getting a log equation, what we do is to differentiate with respect to time. So here we differentiate our kappa with respect to t. Sorry, this is not supposed to be x, it is supposed to be t. So this, as you know, as I explained to you in the Harrod-Domar growth model, how we differentiate natural logs. So here we come up with 1 over kappa dt, not dy, being equal to 1 over k if you are differentiating ln k, 1 over k dk dt, minus, now we come back with the brackets here, minus 1 over a dA dt, plus 1, if you differentiate ln L, we come up with 1 over L dL dt. We move on to another step. Now I told you this is just a typing error. This is supposed to be the kappa dt, not dy dx. No, that was a typing error. So this is we come up with something as 1 over kappa. Remember, if we have the kappa dt, it's more of change in kappa. Dk dt is change in k. The A dt is change in A, the L dt is change in L. So what I did here is to represent this dk dt with this, with a change in k, dt dA with a change in A, just to simplify. I came up with this equation. So if I multiply 1 over kappa times change in kappa, it's this, change in kappa over kappa. If I multiply 1 over k times change in k, I come up with change in k over k, then r minus 1 over a times change in a gives us change in a over a. 1 over L times change in L gives us change in L over L. Now, here I have a but, saying that but what is our change in k? Remember, when you were looking at the key equations that I told you about, we said that our first equation was the capital accumulation equation, and it shows that our change in k is defined as I minus sigma kt. Now if we come here, we are having our new equation as change in kappa over kappa is equal to change in k over k minus change in a over a plus change in L over L. So what we do is to represent our change in k with the I minus sigma kt, because we said this change in k is capital accumulation and it is I minus sigma k. Now we also note that if we have, let's say, the A over A, or if we have a change in A over A, if we have a change in A over A is a growth rate, that is the growth rate of knowledge or technology. Our change in L over L is the growth rate of labor, which we represent by L. So after noting all those, we come up with a new equation from this last equation that we had. We substitute in for change in k, we also substitute in for change in a over a, we also substitute in for change in L over L. We come up with change in kappa over kappa. This is change in capital per effective worker over capital per effective worker is equal to investments minus sigma k over k. Remember, we substituted only with the numerator, not the denominator. The change in k only the numerator, not denominator. Then minus, we represented this with a g. Then we represented the whole of this with an n. So this is our new equation. Now, after coming up with that new equation, we have to note a few things, or we do something that is really not so difficult. What I do here is, because you are seeing I minus sigma k over k, it means that this k divides the I, it also divides the sigma k. So what I do is to separate them. That's why I'm having change in kappa over kappa is equal to I over k minus sigma k over the k, then minus our g plus n. If we divide sigma k over k, the k will go and we remain with only sigma. So that's why we are having here our next step, or with the second equation, we are having change in kappa over kappa is equal to I over k minus. Remember, now if you remain with this sigma, it has a minus sign, right? So we add it to these brackets, we come up with I over k minus sigma plus g plus n, in that if we take out this sigma out of the brackets, it becomes negative again. Now, after doing that, you may wonder what is our next step. Now, our next step, as I told you in my previous tutorial, if we get a given variable, the same variable, multiply it and divide it by the same variable, you get the same thing. Like if we have change in kappa over kappa, if I'm to multiply it by AL and also divide it by AL, I'll remain with change in kappa over kappa. If I multiply sigma by AL, also divide it by AL, of course the AL will cancel out, I will still remain with sigma. If I multiply the G by AL and divide it by AL, still I remain with G because the ALs will cancel out. The same goes for the N. Now, it's what I did in this equation. Now, here remember I have I over K, right? So also it is the same, like it is the same thing I did here. Also multiplied the I over K by AL, also divided it by AL. What I changed is the appearance or the order. It doesn't matter, it still gives me the same thing. If I say I over AL times AL over K, it is the same as I having I over K times AL over AL. Remember, if you look at multiplication, the order doesn't matter. So here I also multiplied. Here these are remaining the same because I told you they will cancel out, and I'm having this. Remember, I told you I over AL is what? Is the small I, or it is investment by effective worker. Now I also told you that K over AL is capital per effective worker, and we represented that with this kappa, or which is as a small k, right? So I come up with, so this I over AL becomes small I. AL over K, it's like we are having an inverse of the kappa, of the capital per effective worker. So it's more of we are having 1 over kappa. That's why I come up with the final thing as change in kappa over kappa is equal to our small I, which is representing 1 over AL over this I said this gives us 1 over kappa. If I multiply 1 over kappa times I, of course I'll get I over kappa, then minus R sigma plus G plus N. Now our next step from this equation here, our next step will be to multiply both sides by kappa. Now if we multiply both sides by kappa, change in kappa over kappa times kappa being equal to I over kappa times kappa minus sigma plus g plus a, this the entire brackets by kappa. What happens is, if we multiply change in kappa over kappa times kappa, of course we shall remain with change in kappa because the kappa will go with what we multiplied it with. Then I over kappa, if we multiply it by kappa, of course the kappas will go and remain with I, and here we shall remain with sigma plus g plus n times the kappa. So after multiplying by kappa, we come up with change in kappa is equal to small I minus sigma plus g plus n times the kappa. But remember, we said that the market clears, and we say that it clears at a point where our savings are equal to investments. Our savings are equal to investments. But remember, we said that savings are equal to small s y, right? One of the assumptions was savings is a fixed proportion of income, right? So if we said that our income now, after turning this into per effective worker terms, we say that now our output, which is now output per effective worker, is equal to kappa alpha, right? And we are saying that our savings s is equal to small sy. Now our small y is what? Is k alpha. So meaning that our output per effective worker is determined by capital per effective worker. Small y is a function of this kappa. So what happens is, it implies that our savings are equal to the small s, a function of what? Of k. This f, a function of k, just represents the what? The y. So that's why here I'm saying we said the market clears, s is equal to I, but our s is also equal to s, a function of k. So meaning that now we have this equation, change in kappa is equal to s, a function of k, minus sigma plus g plus n kappa times the entire bracket times kappa. Now when you are looking at the Solow'S growth model, this model assumed a steady state point, or it's more of an equilibrium point. Now at the steady state equilibrium, or at the steady state, we assume, or they assumed, that our change in capital per effective worker, which is the kappa, is equal to 0. So the steady state condition is our change in capital per effective worker is equal to 0. So what happens is, since this is equal to 0, it means that we are going to equate the entire equation to 0. So therefore, since change in kappa is 0, we represent it with a 0, 0 equaling 2s, a function of kappa, minus sigma plus g plus n times kappa. So if this crosses the equal sign, we come up with s, a function of k, being equal to sigma plus g plus n kappa. So now our equation 6 is the Solow'S equation, or the Solow'S model. The left hand side represents our net investments, and the right hand side represents the break-even investments. So the Solow'S equation, or the Solow'S model, is such that we assume that our net investments, or you can say that the economy's savings, are equal to the break-even investments. So equation 6 is the Solow'S equation, or the Solow'S model. Now, if you critically looked or watched the first tutorial on the Harrod-Domar growth model, and you've also seen the Solow'S growth model, you realize that both these models talk about talk about savings as something that influence the growth rate of a given economy. Now, the major difference here is in this Solow'S growth model, they assumed that the factor inputs are subject to diminishing marginal returns, which was not assumed in the Harrod-Domar growth model. Now, also in the Harrod-Domar growth model, if you are looking at the capital per effective worker, the capital output ratio, the capital output ratio in the Harrod-Domar growth model was assumed to be fixed. That was the theta. Now, in this case, the capital output ratio in the Solow'S growth model is not fixed. We will see that it varies because our capital stock or our capital per effective worker does vary. So if you tune on to my next tutorial that will come in, we shall prove that in the Solow'S model, the theta or the capital output ratio actually is not fixed, but it varies. Now, this means that in the Solow'S growth model, if as long as a country increases its savings rate, it means that that country will attain growth that is forever. But in the Solow'S growth model, growth will not be forever because the model assumes that we shall have a steady state period, or we shall have a given equilibrium where a country will eventually be. If you're below the steady state equilibrium, it means that you will be moving towards it at a certain point. If you are above, it means that eventually you like an economy will decline and go back to the steady state level. Take an example of China. If you look at China, previously it is an economy that has grown, and if we are to represent it graphically, you see that it was above the steady state point, or it was above equilibrium. Now, the fact that at present situation we are seeing that it is facing a lot of depreciation, it's like more of the capital, more of the investments have depreciated, more of the capital has depreciated. We are seeing that they are declining towards the steady state. So growth will not be forever according to the Solow'S growth model, because one, we have diminishing marginal returns, and then our capital output ratio is not fixed. So this is not all with the Solow'S growth model. We still have to go ahead and look at other things like the golden rule level of capital. We also have to go ahead and look at the implications of both models, the Harrod-Domar growth model and the Solow'S growth model. We have to see how relevant they are, and there are so many other things, such that we conclude the exogenous growth theories and move on to the endogenous growth theories. I thank you for tuning on to this tutorial. Please subscribe to the channel if you have not, and wait for the next tutorial. Thank you.